Imagine a world beneath your feet, a planet you thought you knew, suddenly revealing its deepest, most unsettling secrets. From the very ground we walk on to the invisible forces that shape our existence, Earth is undergoing transformations that defy our understanding. What if the familiar rhythm of our days is subtly shifting, driven by unseen mechanisms deep within our world? What if the very fabric of our reality is being rewoven by phenomena so profound they challenge everything we thought we knew about our home? Prepare to journey into the heart of these mysteries, to uncover the strange, undeniable truths happening on Earth right now. If you're ready to have your perception of our planet forever changed, hit that like button and join us as we delve into the astonishing, the inexplicable, and the truly shocking. For millennia, the Earth has been a steadfast clock, its rotation a constant, predictable rhythm dictating the ebb and flow of day and night. We've built our civilizations, our calendars, our very sense of time around this cosmic pendulum. But what if that pendulum is starting to swing erratically? What if the Earth, our ancient reliable home, is subtly accelerating, shaving precious milliseconds off our days, and hinting at profound changes beneath its surface? Consider a child on a merry-go-round. When they pull their arms in close to their body, they spin faster. Extend them, and they slow down. This simple principle, the conservation of angular momentum, governs everything from pirouetting ice skaters to the swirling galaxies. Now, imagine our entire planet as that child, and something deep within its colossal mass is pulling its arms in. On June 29th, 2022, the Earth completed its rotation 1.59 milliseconds faster than its average 24-hour cycle, marking the shortest day ever recorded since atomic clocks began their precise measurements. This wasn't an isolated incident. Since 2016, our planet has been consistently breaking records for short days, a reversal of a multi-billion-year trend of gradual slowing. For eons, the moon's gravitational tug has been a cosmic break, slowly but surely lengthening our days. Now, something else is at play, a powerful internal force that is overriding this ancient celestial dance. This seemingly minuscule change, a mere fraction of a second, might seem insignificant in our daily lives. We don't wake up feeling the Earth spinning faster, nor do our clocks suddenly jump ahead. Yet, in the realm of ultra-precise technology, these tiny shifts have monumental implications. Our global positioning systems, satellite communications, financial networks, and even the internet itself rely on an incredibly accurate, synchronized global timescale. A negative leap second, where we would have to subtract a second from official clocks for the first time in history, is now a real possibility. This isn't just a technical glitch. It's a profound challenge to the very infrastructure of our modern world, built on the assumption of a predictable, stable Earth. It's a stark reminder that even the most fundamental constants of our existence are subject to the Earth's mysterious, internal dynamics. What could be driving such a dramatic shift? The answer, it seems, lies far beneath our feet, in the churning, molten heart of our world. Deep beneath the Earth's crust, far beyond the reach of human eyes or instruments, lies a world of unimaginable pressure and heat, our planet's inner core. A solid ball of iron and nickel, roughly the size of Pluto. It floats within a sea of molten outer core, spinning independently, a colossal gear in the Earth's intricate machinery. For decades, Scientists believed this inner core rotated steadily eastward, a slow, majestic dance that influenced our planet's magnetic field. But recent seismic data has unveiled a startling revelation. The inner core has not only slowed its rotation, but may now be turning in the opposite direction. To grasp the magnitude of this, imagine a colossal, invisible gyroscope at the very heart of our world. Its steady spin has been a constant, a silent partner in Earth's geological processes. Now, that gyroscope is faltering, even reversing its direction. Seismic waves generated by earthquakes act like cosmic sonar, traveling through the Earth's layers and revealing their secrets. By meticulously analyzing these waves, scientists observed that around 2009, the inner core's rotation relative to the surface began to slow. And more recently, evidence suggests it has entered a new phase, potentially rotating westward. This isn't a sudden, catastrophic lurch, but a gradual, cyclical shift, a planetary heartbeat with a rhythm spanning decades. The implications are profound. The inner core's rotation is intimately linked to the geodynamo, the process that generates Earth's protective magnetic field. A change in its spin could influence the strength and stability of this shield, which deflects harmful solar radiation and makes life on Earth possible. It's a reminder that even the most seemingly stable parts of our planet are in a constant state of flux, driven by forces we are only just beginning to comprehend. What other secrets does this deep, hidden world hold, and how might its subtle shifts impact our lives on the surface? Above us, an invisible shield protects all life on Earth. This is our planet's magnetic field, a vast, dynamic force field generated by the churning liquid iron in its core. It deflects harmful solar winds and cosmic radiation, making our atmosphere habitable and our technology functional. Without it, our planet would be a barren wasteland, constantly bombarded by deadly particles. But this shield, too, is showing signs of strain, revealing a peculiar vulnerability known as the South Atlantic Anomaly. Imagine a tiny, almost imperceptible tear in a protective bubble. That's what the South Atlantic Anomaly, or SAA, represents. A massive weak spot in Earth's magnetic field, stretching from South America across the Atlantic Ocean to Africa. In this region, the magnetic field is significantly weaker, allowing charged particles from space to dip closer to the Earth's surface. For us on the ground, it's largely unnoticeable, but for satellites orbiting above, it's a hazardous zone. As spacecraft pass through the SAA, they are exposed to higher levels of radiation, which can cause malfunctions, data corruption, and even permanent damage to their electronics. It's like a cosmic pothole, constantly challenging the resilience of our technological infrastructure. What's even more concerning is that this anomaly is not static. It's deepening, expanding, and recent data suggests it might even be splitting into two distinct centers. This isn't just a localized oddity. It's a symptom of larger, more profound changes within the geodynamo, the very engine that powers our magnetic shield. Scientists are closely monitoring the SAA, as its behavior could be a precursor to a complete geomagnetic reversal, an event where the Earth's magnetic poles flip, a phenomenon that has occurred many times throughout our planet's history, with potentially dramatic consequences for life and technology. Our planet is not a perfectly stable sphere. It wobbles and shifts on its axis, a dance influenced by the distribution of its mass. For centuries, scientists have observed the Earth's geographic North Pole drifting, a slow, meandering journey across the Arctic. But around the year 2000, something unexpected happened. The North Pole abruptly changed its course. Instead of continuing its drift towards Canada, it veered sharply towards Greenland, and its pace accelerated significantly. Imagine a spinning top, perfectly balanced, suddenly altering its axis of rotation without any visible external force. This isn't just a minor adjustment. It's a significant deviation from its historical path, hinting at powerful, unseen forces at play within our planet. This shift in polar drift is intimately connected to another enigmatic phenomenon, the Chandler Wobble. For over a century, scientists have tracked this subtle, rhythmic wobble of the Earth's rotation axis, a predictable oscillation with a period of about 433 days. It's a natural consequence of the Earth's slightly imperfect shape and the dynamic interplay of its fluid layers. But between 2000 and 2005, this long-standing, predictable rhythm nearly vanished. The Chandler Wobble, a planetary heartbeat that had been ticking consistently for over 100 years, suddenly flatlined. Imagine a perfectly tuned musical instrument suddenly falling silent, its familiar melody replaced by an eerie quiet. This suppression of the Chandler Wobble, coupled with the accelerated polar drift, points to a profound redistribution of mass within the Earth, likely driven by the melting of glaciers and ice sheets and the subsequent shift of vast quantities of water. As colossal amounts of ice melt, the water flows into the oceans, subtly altering the planet's moment of inertia, much like our merry-go-round child extending their arms. These seemingly distant events, melting ice and a wobbling Earth, are intricately linked, revealing a planet in constant dynamic flux, responding to both internal and external pressures in ways we are only just beginning to decipher. What other hidden connections lie beneath the surface of these strange phenomena, and what do they portend for the future of our world? These individual phenomena, the accelerating rotation, the shifting inner core, the weakening magnetic field, the wandering poles, and the suppressed wobble, might seem like isolated curiosities. But what if they are not? What if they are all interconnected, threads in a grand, complex tapestry woven by the Earth itself, signaling a profound shift in our planet's fundamental state? Imagine a symphony orchestra where each instrument plays its part, contributing to a harmonious whole. Now, imagine several instruments suddenly changing their tune, their rhythm, or even their direction. The result would be a cacophony, a disruption of the established order. Our Earth, in its own majestic way, is performing such a symphony, and the recent dissonances are demanding our attention. Scientists are now piecing together a comprehensive picture, synthesizing data from 7 independent areas: the core's rotation, the magnetic field's intensity, the surface's speed, the loss of ice, the drift of the poles, the circulation of the oceans, and even atmospheric patterns. What emerges is a portrait of a planet in transition, moving away from the stable, predictable state of the Holocene, the geological epoch that has cradled human civilization for the last 11,700 years. We have built our entire modern world, our infrastructure, our technology, our very understanding of time and space, on the assumption of a stable Earth. Our global positioning systems, for instance, are calibrated to a precise model of Earth's rotation. When that rotation subtly changes, these systems, and everything that relies on them, face unprecedented challenges. It's like trying to navigate a ship with a compass that's constantly shifting its true north. the implications are not just academic, they are practical, affecting everything from the timing of financial transactions to the accuracy of satellite navigation for airplanes and self-driving cars. This isn't merely a change in climate, though climate change is undoubtedly a significant factor in some of these shifts. This feels like a fundamental recalibration of the world as we know it, a planetary reaction to centuries of unseen pressures. The Earth, in its immense wisdom, is responding, adapting, and evolving. And in doing so, it is challenging our models, our assumptions, and our very place within its grand design. We are witnessing a volatility that defies our traditional understanding, a reminder that the Earth is a living, breathing entity, far more dynamic and mysterious than we often give it credit for. The time bomb isn't just a metaphor anymore, it's a measurement, a tangible shift in the rhythm of our planet. What does this mean for the future? Are we entering a new, unpredictable era where the very ground beneath our feet and the forces above and below it will continue to surprise and challenge us? The journey into these strange phenomena is not just a scientific exploration, it's a profound meditation on our relationship with the planet we call home, and a call to understand its intricate workings before its secrets reshape our world in ways we can barely imagine. Let's delve deeper into this unprecedented acceleration of Earth's rotation. For billions of years, our planet has been gradually slowing down. This deceleration is primarily due to the gravitational dance between Earth and its moon. The moon's pull creates tides, and as these tidal bulges move across the oceans, they drag against the ocean floor, creating friction. This friction acts like a cosmic brake, slowly but steadily transferring angular momentum from Earth to the moon, causing our planet to spin a little slower and the moon to drift a little farther away. It's a cosmic ballet, slow and predictable, that has been playing out for eons, lengthening our days by roughly 2.3 milliseconds per century. This consistent slowing has been meticulously tracked through ancient astronomical records, from Babylonian clay tablets documenting eclipses to medieval European observations. These historical records, combined with modern atomic clock measurements, paint a clear picture of a planet in a long-term deceleration. But then, something shifted. Around 2016, this ancient trend began to reverse. Suddenly, Earth started spinning faster, not slower. The shortest day on record, June 29th, 2022, was not an anomaly, but a peak in a new, accelerating trend. This is where the analogy of the figure skater becomes even more crucial. For Earth to speed up, mass must be moving closer to its axis of rotation. What could be causing such a colossal redistribution of mass? Scientists point to a complex interplay of factors, both on the surface and deep within the planet. One significant contributor is the melting of glaciers and ice sheets. As vast quantities of ice, particularly at the poles, melt and flow into the oceans, this mass is redistributed from higher latitudes towards the equator. Imagine a spinning top with a blob of clay near its top. If that clay slides down towards the middle, the top spins faster. Similarly, as ice melts and water moves towards the equator, it reduces Earth's moment of inertia, causing it to spin faster. This is a direct, measurable consequence of climate change, a human-induced factor now actively influencing the very rotation of our planet. But surface changes alone cannot fully account for the observed acceleration. The most profound drivers of Earth's rotation lie far beneath the surface, in the churning, molten heart of our world. Here, in the outer core, a vast ocean of liquid iron and nickel swirls and flows, generating our planet's magnetic field through a process known as the geodynamo. This colossal, self-sustaining dynamo is not just responsible for our protective magnetic shield. It also plays a critical role in regulating Earth's spin. Think of the outer core as a gigantic, turbulent ocean, constantly in motion. The currents within this ocean are driven by convection. As hotter, less dense material rises and cooler, denser material sinks. These complex flows, interacting with Earth's rotation, create powerful electrical currents, which in turn generate magnetic fields. It's a feedback loop, a cosmic engine that has been running for billions of years. But these flows are not always smooth and predictable. They can be chaotic, turbulent, and subject to subtle shifts and changes. And when these flows change, they can exert torques on the solid mantle and crust above, subtly altering the planet's rotation rate. It's like a giant invisible hand gently pushing and pulling on the Earth, influencing its spin from within. The inner core, that solid ball of iron and nickel at the very center of our planet, is intimately connected to this geodynamo. It's not just passively floating in the molten outer core, it's actively interacting with it. The magnetic fields generated in the outer core can exert forces on the inner core, causing it to spin at a different rate than the rest of the planet. This is what scientists refer to as differential rotation. For a long time, it was believed that the inner core spun slightly faster than the Earth's surface, gradually drifting eastward. But as we've seen, recent data suggests a dramatic shift. The inner core has slowed and may even be reversing its direction. This isn't just a curiosity, it's a profound indicator of changes within the geodynamo itself. A change in the inner core's rotation suggests a change in the forces acting upon it, forces generated by the turbulent flows of the outer core. It's a complex, interconnected system where a subtle shift in one component can have ripple effects throughout the entire planet. The Earth, it seems, is a far more dynamic and responsive entity than we ever imagined, constantly adjusting and recalibrating its internal mechanisms in ways that are only just beginning to be understood. And these internal adjustments are now manifesting as tangible, measurable changes on the surface, impacting everything from the length of our days to the very fabric of our technological world. Let's return to the invisible shield that protects us, our planet's magnetic field, and the peculiar vulnerability known as the South Atlantic Anomaly. Imagine a colossal, invisible force field surrounding Earth, a protective bubble that deflects harmful cosmic radiation and solar winds. This shield is generated by the churning, liquid iron in our planet's outer core, a process called the geodynamo. Without this magnetic embrace, our atmosphere would be stripped away, and life as we know it would be impossible. But this shield is not uniform. It has a weak spot, a growing breach that is causing concern among scientists and space agencies alike. The South Atlantic Anomaly, or SAA, is a vast region where the Earth's magnetic field is significantly weaker, allowing charged particles from space to dip much closer to the planet's surface. Picture a leaky roof in a storm. The SAA is a leak in our planetary defense. For those of us on the ground, this phenomenon is largely imperceptible. We don't feel the increased radiation, nor do we see its effects directly. However, for the thousands of satellites orbiting Earth, particularly those in low Earth orbit, the SAA is a treacherous zone. As these spacecraft traverse the anomaly, they are bombarded by high-energy protons and electrons, leading to a host of problems: computer glitches, data corruption, and even permanent damage to sensitive electronic components. It's a constant challenge for satellite operators, requiring them to shut down non-essential systems or even reorient their spacecraft to minimize exposure. This isn't just an inconvenience, it's a significant operational risk for the global infrastructure that relies on these satellites, from GPS navigation and weather forecasting to telecommunications and scientific research. What makes the SAA even more intriguing and concerning is its dynamic nature. It's not a static feature, it's deepening, expanding, and recent observations suggest it might even be splitting into two distinct centers. Imagine that leaky roof not just getting bigger, but also developing new, separate holes. This behavior is a direct reflection of the complex and turbulent processes occurring within the Earth's outer core. The geodynamo, the engine that generates our magnetic field, is in a constant state of flux, and the SAA is a visible manifestation of these internal shifts. Scientists are intensely studying the SAA, not just because of its immediate impact on technology, but because it could be a harbinger of something far more profound: a complete geomagnetic reversal. Throughout Earth's history, the magnetic poles have flipped numerous times, with the North Pole becoming the South Pole and vice versa. While the exact mechanisms and consequences of such an event are still debated, a prolonged period of weakened magnetic field during a reversal could expose Earth to increased radiation, potentially impacting ecosystems and posing significant challenges to our technological civilization. The SAA, therefore, is not just a scientific curiosity. It's a window into the deep, mysterious workings of our planet, and a potent reminder of the delicate balance that sustains life on Earth. Our planet, though seemingly solid and unyielding, is a dynamic, ever-changing entity, constantly adjusting its balance. One of the most subtle yet significant indicators of this planetary dynamism is the phenomenon of polar drift. For centuries, astronomers and geophysicists have meticulously tracked the Earth's geographic North Pole, observing its slow, meandering journey across the Arctic. This drift is not random. It's influenced by the redistribution of mass on and within the planet. Imagine a perfectly balanced spinning top. If you subtly shift a tiny weight on its surface, its axis of rotation will also subtly shift. Earth, in its grander scale, behaves similarly. For much of the 20th century, the North Pole was observed to be drifting steadily towards Canada, a predictable, albeit slow, movement. But around the year 2000, something remarkable occurred. The North Pole abruptly changed its course, veering sharply towards Greenland and accelerating its pace significantly. This wasn't a minor correction. It was a dramatic deviation from its historical trajectory, signaling a profound shift in the forces influencing our planet's orientation in space. This accelerated polar drift is intimately linked to another fascinating and equally enigmatic phenomenon: the Chandler Wobble. Discovered in the late 19th century by Seth Carlo Chandler, this is a subtle, rhythmic oscillation of the Earth's rotation axis, a natural wobble with a period of approximately 433 days. It's a complex dance, a consequence of the Earth's slightly oblate shape and the dynamic interplay of its fluid layers: the oceans, the atmosphere, and the molten outer core. The Chandler Wobble is a planetary heartbeat, a predictable rhythm that has been ticking consistently for over a century, providing scientists with invaluable insights into the Earth's internal dynamics. But between 2000 and 2005, this long-standing, predictable rhythm nearly vanished. The Chandler wobble, a constant companion in our understanding of Earth's rotation, suddenly flatlined, its familiar oscillation suppressed to an unprecedented degree. Imagine a perfectly tuned musical instrument, playing a consistent melody for decades, suddenly falling silent. This suppression, coupled with the accelerated polar drift, points to a massive and rapid redistribution of mass within the Earth, primarily driven by the melting of glaciers and ice sheets. As colossal amounts of ice, particularly in Greenland and Antarctica, melt and flow into the oceans, this vast quantity of water is redistributed across the planet. This shift in mass, though seemingly subtle on a human scale, is enough to alter Earth's moment of inertia, causing its axis of rotation to shift and its wobble to be dampened. It's a powerful, tangible link between human-induced climate change and the fundamental dynamics of our planet, revealing a complex, interconnected system where events on the surface can have profound impacts on the Earth's deep internal workings. These strange phenomena are not just isolated scientific curiosities. They are interconnected pieces of a larger puzzle, revealing a planet in constant dynamic flux, responding to both internal geological forces and external environmental pressures in ways we are only just beginning to comprehend. The Earth, it seems, is a far more sensitive and responsive entity than we ever imagined, constantly adjusting and recalibrating its internal mechanisms in ways that are only just beginning to be understood. And these internal adjustments are now manifesting as tangible, measurable changes on the surface, impacting everything from the length of our days to the very fabric of our technological world. Scientists are now piecing together a comprehensive picture, synthesizing data from 7 independent areas: the core's rotation, the magnetic field's intensity, the surface's speed, the loss of ice, the drift of the poles, the circulation of the oceans, and even atmospheric patterns. What emerges is a portrait of a planet in transition, moving away from the stable, predictable state of the Holocene, the geological epoch that has cradled human civilization for the last 11,700 years. We have built our entire modern world, our infrastructure, our technology, our very understanding of time and space, on the assumption of a stable Earth. Our global positioning systems, for instance, are calibrated to a precise model of Earth's rotation. When that rotation subtly changes, these systems, and everything that relies on them, face unprecedented challenges. It's like trying to navigate a ship with a compass that's constantly shifting its true north. The implications are not just academic, they are practical, affecting everything from the timing of financial transactions to the accuracy of satellite navigation for airplanes and self-driving cars. This isn't merely a changing climate, though climate change is undoubtedly a significant factor in some of these shifts. This feels like a fundamental recalibration of the world as we know it, a planetary reaction to centuries of unseen pressures. The Earth, in its immense wisdom, is responding, adapting, and evolving. And in doing so, it is challenging our models, our assumptions, and our very place within its grand design. We are witnessing a volatility that defies our traditional understanding, a reminder that the Earth is a living, breathing entity, far more dynamic and mysterious than we often give it credit for. The time bomb isn't just a metaphor anymore. It's a measurement, a tangible shift in the rhythm of our planet. What does this mean for the future? Are we entering a new, unpredictable era where the very ground beneath our feet and the forces above and below it will continue to surprise and challenge us? The journey into these strange phenomena is not just a scientific exploration, it's a profound meditation on our relationship with the planet we call home, and a call to understand its intricate workings before its secrets reshape our world in ways we can barely imagine. Let's consider the sheer scale of these transformations. Imagine trying to steer a massive cargo ship, miles long and weighing hundreds of thousands of tons, with a tiny rudder. Now imagine that the currents beneath the ship are suddenly changing direction, and the very composition of the water is shifting. This is a crude analogy for the complexity of Earth's systems. The forces at play are immense, operating on geological timescales. Yet their effects are now becoming apparent within a single human lifetime. The Earth's rotation, for example, is not just a simple spin. It's a delicate balance influenced by everything from the distribution of water in its oceans to the flow of molten metal in its core. When one of these factors changes, the entire system must adjust, often in ways that are difficult to predict. The implications of these phenomena extend far beyond scientific curiosity. They touch upon our very perception of stability and predictability. For centuries, humanity has relied on the Earth's consistent rhythms to build our societies, plan our agriculture, and navigate our world. The sun rises and sets, the seasons change, and the stars wheel across the night sky with a comforting regularity. But if these fundamental rhythms are subtly shifting, what does that mean for our future? What happens when our precise satellite navigation systems, which guide everything from commercial flights to autonomous vehicles, start to encounter discrepancies due to an unpredictable Earth rotation? What happens when the delicate balance of our planet's magnetic field, which protects us from the harsh realities of space, begins to falter in unexpected ways? These are not questions for a distant future. They are questions for now, as scientists race to understand the full scope of these strange phenomena and their potential consequences. Think about the ancient mariners who navigated by the stars, relying on their unchanging positions to guide them across vast oceans. Their world was one of relative constancy, where the celestial sphere provided an immutable map. Our modern world, however, is built on a far more intricate and precise understanding of our planet's position and movement in space. We rely on atomic clocks that measure time with astonishing accuracy, and on global satellite networks that pinpoint our location with centimeter precision. These technologies are the bedrock of our interconnected world, enabling everything from instantaneous global communication to the efficient operation of our financial markets. But what if the very ground beneath these technological marvels is subtly shifting? What if the Earth itself is introducing a new variable into our equations? A variable that challenges the very foundations of our technological civilization. The prospect of a negative leap second, for instance, is not just a technical headache for timekeepers. It's a stark reminder of how deeply intertwined our digital world is with the Earth's physical rhythms. A sudden, unplanned adjustment to global time could have cascading effects, disrupting computer systems, financial transactions, and communication networks worldwide. It's a scenario that highlights our vulnerability, our dependence on a planet that, despite our technological prowess, still holds ultimate sway over our existence. And what of the long-term implications? If the South Atlantic Anomaly continues to expand and deepen, what does that mean for the future of space exploration and satellite technology? Will we need to design more robust, radiation-hardened spacecraft, or will certain orbits become too hazardous to use? If the Earth's inner core continues its unpredictable dance, how might that influence the geodynamo and, by extension, the strength and stability of our magnetic field? Could a prolonged period of magnetic field weakening leave our planet more exposed to solar storms, potentially disrupting power grids and communication systems on a global scale? These are not doomsday scenarios, but legitimate scientific questions that are being actively investigated. The strange phenomena happening on Earth right now are not just isolated events. They are interconnected pieces of a grand, evolving puzzle. A puzzle that challenges us to rethink our relationship with our planet and to understand its intricate workings with a newfound urgency. The Earth is speaking to us, revealing its secrets in subtle yet profound ways. Are we listening? And are we prepared for what it has to tell us? To truly grasp the interconnectedness of these planetary shifts, let's consider a more familiar analogy. Imagine your own body. Every system, from your circulatory to your nervous system, works in concert to maintain a delicate balance. A slight change in one system, say a fever, can have ripple effects throughout your entire being, affecting your energy levels, your cognitive function, and your overall well-being. The Earth, in its immense complexity, functions much like this. Its various geological, atmospheric, and magnetic systems are not isolated. They are constantly interacting, influencing, and responding to one another. When the inner core's rotation shifts, it affects the geodynamo. When the geodynamo changes, it impacts the magnetic field. When the magnetic field weakens, it exposes the surface to more radiation. When ice melts on the surface, it redistributes mass, influencing the planet's rotation and wobble. It's a cascade of cause and effect, a planetary domino effect, where one subtle push can trigger a series of profound transformations. This intricate web of connections highlights a crucial point. Our planet is not a static backdrop against which human history unfolds. It is an active participant, a living entity with its own internal dynamics and responses. For centuries, we have often viewed Earth as a stable, unchanging foundation, a reliable stage for our endeavors. But these strange phenomena are forcing us to confront a different reality. A dynamic, responsive planet that is constantly evolving, often in ways that challenge our assumptions and our technological capabilities. We have built our modern world on the premise of predictability, on the assumption that the fundamental laws governing our planet are constant and well understood. But what if those assumptions are being subtly undermined by the Earth itself? Consider the concept of time. For us, a day is a day, a fixed unit of 24 hours. We schedule our lives, our work, our global communications around this precise measurement. But if the Earth's rotation is subtly accelerating, if our days are becoming infinitesimally shorter, what does that mean for our meticulously synchronized global systems? It's like trying to keep time with a clock that's secretly speeding up, requiring constant, delicate adjustments to prevent chaos. The prospect of a negative leap second where we would have to subtract a second from official clocks, is not just a technical challenge, it's a philosophical one. It forces us to acknowledge that even our most fundamental units of measurement are ultimately tied to the Earth's physical rhythms. Rhythms that are now proving to be far more dynamic than we once believed. This isn't just about correcting clocks, it's about recalibrating our entire relationship with time itself and with the planet that defines it. And what about the invisible shield, our magnetic field? Imagine living in a house with a roof that's slowly deteriorating, developing weak spots and thinning patches. You might not notice it on a sunny day, but when a storm hits, the consequences could be severe. The South Atlantic Anomaly is precisely such a weak spot in Earth's magnetic roof. While it doesn't directly threaten life on the surface, its impact on our satellites is a stark reminder of our dependence on this invisible protection. Our modern world is utterly reliant on these orbiting eyes and ears for everything from weather forecasts that save lives to the financial transactions that drive our global economy. If these satellites are constantly at risk of malfunction or damage due to increased radiation, it introduces a new layer of vulnerability into our technological infrastructure. It's a subtle but persistent threat, a constant reminder that even in the vastness of space, our technological creations are still tethered to the Earth's internal dynamics and its unpredictable magnetic moods. The shifting poles and the suppressed Chandler wobble further underscore this planetary responsiveness. Imagine a child's spinning top, not just wobbling, but also subtly changing the point on the floor around which it spins. And then, imagine that wobble suddenly becoming almost imperceptible. These are not just abstract scientific observations. They are tangible manifestations of massive internal shifts within our planet. The melting of vast ice sheets, driven by a warming climate, is redistributing colossal amounts of water, altering the Earth's moment of inertia and literally changing how it spins and wobbles. It's a powerful feedback loop, where human activity on the surface can trigger profound responses deep within the planet. This isn't just about rising sea levels, it's about a fundamental alteration of Earth's rotational dynamics, a planetary response to the pressures we are exerting upon it. These phenomena force us to confront the idea that our actions have consequences that ripple through the entire Earth system, affecting even the most fundamental aspects of its physical behavior. In essence, these strange phenomena are a planetary symphony of change, a complex interplay of forces that are reshaping our world in subtle yet profound ways. They challenge our assumptions, test our technologies, and demand a deeper understanding of the intricate mechanisms that govern our home. The Earth is not a passive observer. It is an active, dynamic entity, constantly evolving and responding. And in its responses, it reveals secrets that are both awe-inspiring and unsettling, pushing the boundaries of our scientific knowledge and forcing us to reconsider our place within its grand, ever-changing design. The journey into these mysteries is not just about facts and figures. It's about a profound re-evaluation of our relationship with the living planet, and a call to listen more closely to the whispers of change emanating from its depths. How do we even begin to understand these hidden processes, these subtle shifts in a planet so vast and complex? We can't simply drill to the Earth's core, nor can we directly observe the magnetic field's intricate dance. Instead, scientists act as planetary detectives, piecing together clues from a variety of sources, using ingenious methods to probe the Earth's deepest secrets. Imagine trying to understand the inner workings of a colossal, sealed machine by only observing its external movements and listening to its faint hums and vibrations. This is the challenge faced by geophysicists, seismologists, and astrophysicists who dedicate their lives to unraveling Earth's mysteries. One of the most powerful tools in this planetary detective work is seismology. Just as a doctor uses ultrasound to peer inside the human body, seismologists use seismic waves, generated by earthquakes or artificial explosions, to create a picture of Earth's interior. These waves travel through different layers of the Earth at varying speeds, and by meticulously analyzing their arrival times and patterns at seismic stations across the globe, scientists can infer the composition, temperature, and even the movement of material deep within our planet. It was through this seismic sonar that the shocking revelation of the inner core's slowing and potential reversal was made. The subtle changes in how seismic waves passed through the core over decades provided the undeniable evidence of its shifting rotation. It's a testament to human ingenuity, transforming the destructive power of earthquakes into a tool for unprecedented discovery. Another crucial piece of the puzzle comes from satellite observations. Orbiting high above us, satellites equipped with highly sensitive magnetometers continuously map Earth's magnetic field, providing a global, real-time picture of its strength and direction. Missions like the European Space Agency's Swarm constellation are specifically designed to study the geodynamo and the evolution of the magnetic field. It's these satellite measurements that have allowed scientists to track the expansion and deepening of the South Atlantic Anomaly, and to observe its potential splitting. Without these eyes in the sky, we would be largely blind to the subtle but significant changes occurring in our planetary shield. These satellites are not just technological marvels. They are our sentinels, constantly monitoring the health of our planet and providing the data necessary to understand its complex, evolving nature. And then there's the meticulous work of geodesy, the science of measuring Earth's shape, orientation in space, and gravity field. This involves an array of techniques from very long baseline interferometry, VLBI, that uses radio telescopes to measure the Earth's orientation with astonishing precision, to satellite laser ranging, SLR, that tracks the movement of satellites to infer changes in Earth's gravity field and rotation. It's these precise measurements that reveal the subtle changes in Earth's rotation rate, the acceleration of our days, and the wandering of our poles. Imagine trying to measure the minuscule wobble of a spinning top from miles away with incredible accuracy. That's essentially what geodesists do, providing the hard data that confirms these strange phenomena are not just theoretical constructs, but measurable realities. These scientific endeavors, often unseen and unappreciated by the general public, are at the forefront of our understanding of Earth, revealing a planet that is far more dynamic and responsive than we ever imagined. They are the silent guardians of our knowledge, constantly pushing the boundaries of what we know about our home, and preparing us for the challenges and wonders that lie ahead. Let's zoom in on one of the most immediate and tangible consequences of Earth's accelerating rotation: the potential for a negative leap second. For most of human history, our concept of time was intrinsically linked to the Earth's rotation. A day was simply the time it took for the Sun to return to the same position in the sky. But with the advent of atomic clocks in the mid-20th century, we gained a far more precise and stable measure of time. These atomic clocks, which measure time based on the vibrations of atoms, are incredibly accurate, losing or gaining only about 1 second in millions of years. This led to the creation of Coordinated Universal Time, or UTC, the global standard for timekeeping that underpins our entire modern world. However, the Earth's rotation, as we've seen, is not perfectly constant. It wobbles, it slows, and now it's speeding up. To keep UTC synchronized with the Earth's actual rotation, a system of leap seconds was introduced. Since 1972, 27 positive leap seconds have been added to UTC, typically at the end of June or December, to account for the Earth's gradual slowing. It's like occasionally adding an extra minute to a clock to keep it in sync with a slightly slower grandfather clock. These adjustments, while seemingly minor, are complex and require careful coordination across global systems. But now, for the first time in history, we face the unprecedented possibility of a negative leap second. This would mean subtracting a second from UTC, essentially making a day 1 second shorter. Imagine the global clock suddenly skipping a beat, jumping from 23:59:58 directly to 00:00:00. What could possibly go wrong? For most people, a missing second might seem utterly inconsequential, but in the hyper-connected, ultra-precise world of modern technology, it could be catastrophic. Consider the intricate dance of global financial markets, where billions of dollars change hands in milliseconds and transactions are time-stamped with incredible accuracy. A sudden, unplanned subtraction of a second could throw these systems into disarray, leading to errors, data inconsistencies, and potentially massive financial losses. Think of the complex algorithms that govern high-frequency trading, or the synchronized networks that manage global logistics and supply chains. These systems are designed to operate with nanosecond precision. A 1-second discrepancy could be akin to a digital earthquake, causing widespread disruption and instability. Beyond finance, critical infrastructure like satellite navigation systems, power grids, and telecommunications networks are also vulnerable. GPS satellites, for example, rely on extremely precise timing signals to determine location. If the ground-based atomic clocks and the satellite clocks suddenly fall out of sync, even by a second, it could lead to significant errors in positioning, impacting everything from commercial aviation to autonomous vehicles. Imagine an airplane's navigation system suddenly miscalculating its position by hundreds of meters, or a self-driving car momentarily losing its bearings. The potential for chaos and danger is immense. It's a stark reminder that our technological advancements, while incredible, are built upon a foundation of natural rhythms that we are only just beginning to fully comprehend and, in some cases, struggle to control. The negative leap second is not just a technical challenge, it's a profound illustration of how deeply intertwined our digital world is with the Earth's physical rhythms, and how a seemingly insignificant planetary shift can have cascading effects across our entire technological civilization. It forces us to confront our own technological hubris, reminding us that even with our most advanced tools, we are still ultimately passengers on a dynamic, unpredictable planet. Let's return to the Earth's enigmatic heart, the inner core, and its astonishing dance. Imagine for a moment a colossal, hidden engine deep within our planet. A silent powerhouse that has been steadily turning for billions of years. For us, living on the surface, its movements are imperceptible, yet its influence is profound. It's like the intricate gears of a master clock, hidden from view but dictating the rhythm of everything around it. For decades, scientists believed this inner core, a solid ball of iron and nickel roughly the size of Pluto, spun consistently eastward, slightly faster than the rest of the planet. This differential rotation was a cornerstone of our understanding of Earth's internal dynamics. A slow, majestic pirouette that helped generate our planet's life-sustaining magnetic field. But then, the data began to whisper a different story. Seismic waves, those echoes from deep within the Earth, started to reveal a change in the inner core's rhythm. Imagine listening to the steady tick-tock of that master clock, only to notice that the tick-tock is gradually slowing, becoming erratic, and then, astonishingly, seems to reverse direction. This is the essence of what scientists observed around 2009. The inner core's rotation relative to the surface began to decelerate, and more recently, evidence suggests it has entered a new phase, potentially rotating westward. This isn't a sudden, violent jolt, but a gradual, cyclical shift, a planetary heartbeat with a rhythm spanning decades, perhaps even 60 to 70 years. It's a profound recalibration of our planet's deepest engine. To understand the significance of this, we need to appreciate the delicate balance within Earth's interior. The inner core is suspended within the liquid outer core, a vast ocean of molten iron and nickel. The interaction between these two layers, driven by convection and Earth's rotation, creates the geodynamo, the very mechanism that generates our magnetic field. Think of it as a complex, self-sustaining electrical generator. The inner core's rotation is not merely a passive movement. It's an active participant in this generation process. Changes in its spin can influence the flow patterns in the liquid outer core, which in turn affects the strength and stability of the magnetic field that shields us from the harsh realities of space. It's a cosmic feedback loop, where the deepest parts of our planet are intimately connected to the conditions on its surface. The implications of this inner core reversal are still being actively investigated, but they are far-reaching. A change in the inner core's rotation could alter the dynamics of the geodynamo, potentially leading to shifts in the magnetic field's strength and configuration. While a complete magnetic pole reversal is a natural geological event that has occurred many times in Earth's history, a prolonged period of magnetic field weakening during such a transition could expose our planet to increased solar radiation, impacting everything from our technological infrastructure to the delicate balance of ecosystems. It's a reminder that the Earth is a living, breathing system, constantly adjusting and evolving, and its deepest secrets hold profound implications for our existence. The inner core, once thought to be a predictable, steady engine, is now revealing itself to be a dynamic, responsive component of our planet, capable of surprising shifts that challenge our understanding and demand our attention. Let's delve deeper into the South Atlantic Anomaly, that peculiar weak spot in our planet's magnetic shield. While its immediate effects are most keenly felt by our orbiting technology, the existence and behavior of the SAA offer a crucial window into the larger, more profound story of Earth's magnetic field. Imagine a vast invisible force field generated by the churning liquid iron in our planet's outer core. This geodynamo, as scientists call it, is a colossal, self-sustaining engine that has been running for billions of years, creating the magnetic field that envelops our planet. This field is not just a scientific curiosity, it is a fundamental prerequisite for life on Earth. It deflects the constant barrage of charged particles from the Sun, the solar wind, and cosmic rays from deep space, preventing them from stripping away our atmosphere and irradiating the surface. Without this protective bubble, Earth would be a barren, lifeless world, much like Mars, which lost its magnetic field billions of years ago and subsequently its atmosphere. The SAA, therefore, is not just a technical nuisance for satellites. It's a tangible manifestation of the dynamic and sometimes unpredictable nature of this life-sustaining shield. In this region, the magnetic field strength is significantly reduced, allowing energetic particles to penetrate deeper into the atmosphere. While these particles are still largely absorbed by the upper atmosphere before reaching the surface, prolonged exposure to a weakening field could have subtle, long-term effects. Some research suggests a potential link between magnetic field fluctuations and changes in cloud formation, or even subtle impacts on migratory animals that use Earth's magnetic field for navigation. These are areas of active research, but they highlight the intricate and often unseen ways in which our planet's magnetic environment influences life itself. What makes the SAA particularly compelling is its potential role as a precursor to a complete geomagnetic reversal. Throughout Earth's history, the magnetic poles have flipped numerous times, with the North Pole becoming the South Pole and vice versa. These reversals are not instantaneous events. They unfold over thousands of years, during which the magnetic field weakens significantly, becomes more complex, and can even exhibit multiple poles. The last full reversal, known as the Brunhes-Matuyama reversal, occurred about 780,000 years ago. While we are not currently in a full reversal, the behavior of the SAA, its deepening, expansion, and potential splitting, is consistent with patterns observed during past periods of magnetic instability that preceded reversals. Imagine a complex dance where the magnetic field is not just weakening, but also becoming more chaotic, with multiple, smaller magnetic poles emerging and shifting. This is what scientists envision during a reversal, and the SAA might be an early warning sign of such a grand planetary event. During a prolonged period of magnetic field weakening, Earth would be more exposed to solar storms and cosmic radiation. While our atmosphere would still provide significant protection, there could be an increase in ground-level radiation, potentially impacting human health and increasing the incidence of certain cancers. More immediately, a severely weakened magnetic field would wreak havoc on our technological infrastructure. Power grids could experience widespread blackouts due to induced currents from solar storms. Satellite communications, GPS, and even terrestrial radio transmissions could be severely disrupted or rendered inoperable. It's a scenario that forces us to confront our profound dependence on an invisible shield that we often take for granted. The SAA, therefore, is not just a localized anomaly. It's a potent reminder of the Earth's deep, internal processes and their capacity to shape our world in ways that are both awe-inspiring and potentially disruptive. It challenges us to understand these phenomena not just as scientific curiosities, but as fundamental aspects of our planetary home that demand our attention and respect. These strange phenomena, while rooted in complex geophysics, are not merely abstract scientific curiosities. They have profound implications for humanity, challenging our technological prowess, our societal structures, and even our psychological sense of security. For millennia, the Earth has been our stable anchor, a predictable stage for the unfolding drama of human civilization. But what happens when that anchor begins to shift? When the very ground beneath our feet and the invisible forces that protect us become less predictable? The psychological impact of living on a planet that is subtly yet undeniably changing its fundamental rhythms is something we are only beginning to grapple with. It can evoke a sense of unease, a feeling that the familiar order of the cosmos is being disrupted, forcing us to confront our own vulnerability in the face of planetary forces far beyond our control. Consider the societal implications. Our globalized world is built on interconnected systems that rely on precision and predictability. From the synchronization of global financial markets to the accurate navigation of international shipping and air travel, every aspect of modern life is intertwined with the Earth's rotational stability and magnetic protection. If these fundamental parameters become more erratic, the ripple effects could be far-reaching. Imagine the challenges of maintaining a global time standard when the Earth's rotation is constantly fluctuating, requiring frequent and potentially disruptive adjustments. What if the increased radiation exposure in the South Atlantic Anomaly forces satellite operators to reroute orbits or invest in significantly more expensive, radiation-hardened technology, driving up costs and potentially limiting access to vital satellite services? These are not just technical hurdles. They are economic and geopolitical challenges that demand international cooperation and innovative solutions. Furthermore, these phenomena underscore the urgent need for a deeper, more holistic understanding of our planet. For too long, humanity has often viewed Earth as an inexhaustible resource, a passive entity to be exploited. But these recent discoveries reveal a dynamic, responsive, and incredibly complex system that is constantly adjusting and evolving. The Earth is not just a collection of inert rocks and water. It is a living, breathing entity with its own internal processes and feedback loops. Our actions on the surface, from the burning of fossil fuels that contributes to ice melt, to the construction of massive infrastructure that subtly alters mass distribution, can have profound and often unforeseen consequences on the planet's deepest workings. It's a powerful reminder that we are not separate from nature. We are an integral part of it, and our destiny is inextricably linked to the health and stability of our planetary home. The journey into these strange phenomena is, therefore, more than just a scientific expedition. It is a philosophical inquiry, a call to reevaluate our relationship with the Earth, and a challenge to adapt our technologies and our societies to a future that may be far less predictable than our past. The Earth is speaking to us, revealing its secrets in subtle yet profound ways. Are we listening? And are we prepared for what it has to tell us? The answers to these questions will define our future as we navigate an era where the very foundations of our world are undergoing a silent yet revolutionary transformation. The strange phenomena happening on Earth right now are not just facts. They are a narrative, a story of a planet in flux, and a testament to the enduring mysteries that lie beneath our feet and above our heads. And as we continue to unravel these mysteries, we are forced to confront the most profound question of all. What does it truly mean to be human on a dynamic, ever-changing Earth? One of the most unsettling conclusions emerging from the study of these strange phenomena is that Earth appears to be transitioning into what scientists call a non-stationary regime. For all of human history, and indeed for the vast majority of geological time, our planet has operated within certain predictable parameters. We've had ice ages and warm periods, volcanic eruptions and continental drifts, but these events, while dramatic, have largely occurred within a stable framework. The Holocene epoch, the last 11,700 years, has been a period of remarkable climatic and geological stability, allowing human civilization to flourish. We built our cities, developed our agriculture, and designed our technologies based on the assumption that the Earth's fundamental rhythms, its rotation, its magnetic field, its climate, would remain largely constant. But this assumption, it seems, is now being challenged. Imagine building a magnificent skyscraper on what you believe to be solid bedrock, only to discover that the bedrock itself is subtly shifting, vibrating, and even changing its composition. This is the challenge we face in a non-stationary Earth. Our modern infrastructure, from the intricate network of fiber optic cables that carry our digital information to the massive dams that hold back billions of tons of water, is designed with specific planetary parameters in mind. Take, for instance, the precise calibration of our global positioning systems. These systems, which guide everything from your smartphone's navigation to precision agriculture and autonomous vehicles, rely on an incredibly accurate model of Earth's rotation and gravity. If the Earth's rotation rate is constantly fluctuating, if its poles are wandering more erratically, and if its magnetic field is weakening in unpredictable ways, then the very foundations of these systems become unstable. It's like trying to hit a moving target with a fixed aim. Constant recalibration and adaptation become necessary, introducing complexities and vulnerabilities that were previously unimaginable. The concept of a negative leap second, which we discussed earlier, is a perfect illustration of this challenge. It's not just a technical fix, it's a symptom of a deeper issue. Our planet is no longer behaving within the narrow, predictable bounds that our technologies were designed for. The financial markets, which operate on nanosecond precision, could face unprecedented disruptions. Power grids, already vulnerable to solar storms, could become even more susceptible to outages if the magnetic shield continues to weaken. Even the very act of communicating across vast distances, which relies on the stable propagation of radio waves through Earth's atmosphere and magnetic field, could be affected. It's a subtle erosion of predictability, a gradual undermining of the assumptions that underpin our technological civilization. The Earth, in its silent, majestic way, is reminding us that it is the ultimate architect, and we are merely tenants, subject to its grand design. This transition to a non-stationary regime is not necessarily a harbinger of immediate catastrophe, but it is a call for profound adaptation. It demands that we rethink our relationship with the planet, moving from a mindset of control and exploitation to one of understanding and coexistence. It forces us to design more resilient technologies, more flexible infrastructure, and more adaptive societal systems that can withstand and respond to a planet in flux. The strange phenomena happening on Earth right now are not just isolated events. They are interconnected signals, a planetary symphony of change that is urging us to listen, to learn, and to evolve. The future, it seems, will be defined not by our ability to conquer nature, but by our capacity to live in harmony with its dynamic, unpredictable rhythms. And in this grand cosmic dance, the Earth remains the lead, constantly surprising us with its power, its mystery, and its profound capacity for transformation. Let's take a moment to truly internalize the scale of these changes. Imagine standing on a vast ancient clock face, its hands moving with such deliberate slowness that their motion is imperceptible to the naked eye. For eons, this clock has kept perfect time, its rhythm a constant against the backdrop of the cosmos. Now, imagine a subtle, almost imperceptible tremor running through the gears, causing the hands to subtly accelerate, then hesitate, then perhaps even reverse their course. This is the Earth, our planetary clock, and we are standing on its face, witnessing a shift in its fundamental rhythm. The beauty of this perspective lies in its ability to ground the abstract in the tangible, to take the colossal and make it relatable to our human experience. Consider the Earth's inner core, that solid ball of iron and nickel, roughly the size of Pluto, spinning within a sea of molten metal. It's a world within a world, a planetary engine that we can never directly see or touch. Yet, its movements, its subtle shifts in rotation, are now being deciphered through the echoes of earthquakes, like listening to the heartbeat of a giant from across a vast chasm. Imagine a master conductor leading an orchestra of unimaginable power, whose subtle gestures dictate the very tempo of our planet. For billions of years, this conductor has maintained a steady rhythm. But now, the baton is wavering, the tempo is changing, and the entire planetary symphony is responding. This grounding analogy allows us to connect with the immense, abstract forces at play, to feel the subtle tremors of change that ripple from the Earth's deepest heart to its outermost reaches. And what of the invisible shield, our magnetic field, that protective bubble that cradles all life on Earth? Imagine a medieval castle, its mighty walls and towering ramparts designed to withstand any assault. This is our magnetic field, a formidable defense against the harsh realities of space. But now, imagine a section of that wall, a vast stretch of its formidable defenses, subtly thinning, becoming porous, allowing tiny, energetic arrows to penetrate its once impenetrable facade. This is the South Atlantic Anomaly, a growing breach in our planetary fortress. While we, the inhabitants within the castle, may not feel the direct impact of these arrows, the sentinels on the ramparts, our satellites, are constantly under fire, their delicate mechanisms vulnerable to the increased bombardment. This contrast between our perceived safety and the unseen vulnerability of our planetary defenses creates a powerful narrative tension, drawing us deeper into the story of Earth's strange phenomena. The wandering poles and the suppressed Chandler wobble further emphasize this dynamic interplay between the colossal and the intimate. These strange phenomena are not just isolated scientific curiosities. They are interconnected pieces of a larger puzzle, revealing a planet in constant dynamic flux, responding to both internal geological forces and external environmental pressures in ways we are only just beginning to comprehend. The Earth, it seems, is a far more sensitive and responsive entity than we ever imagined, constantly adjusting and recalibrating its internal mechanisms in ways that are only just beginning to be understood. And these internal adjustments are now manifesting as tangible, measurable changes on the surface, impacting everything from the length of our days to the very fabric of our technological world. The narrative here is one of discovery, of unveiling hidden truths, and of a planet that continues to surprise and challenge our understanding. It's a story that unfolds on a grand cosmic stage, yet its implications resonate deeply with our human experience, forcing us to reconsider our place within this dynamic, ever-evolving cosmos. So, what does this all mean for us, the inhabitants of this dynamic, ever-changing planet? These strange phenomena are not just isolated scientific curiosities. They are a profound call to attention, a planetary message delivered in the language of geology, physics, and cosmic rhythms. For too long, humanity has often viewed Earth as a static stage, a backdrop against which our dramas unfold. We have built our civilizations, our technologies, and our very understanding of existence on the assumption of a predictable, unchanging world. But the Earth, in its immense wisdom, is now challenging that assumption, revealing itself to be a far more active, responsive, and even unpredictable entity than we ever imagined. This shift in perspective is not merely academic. It has tangible, real-world consequences. The accelerating rotation, the shifting inner core, the weakening magnetic field, the wandering poles, the suppressed wobble. These are not just data points for scientists to analyze. They are fundamental alterations to the very fabric of our planetary home. Alterations that demand our attention and our adaptation. Imagine a species that has evolved to thrive in a specific environment, only to find that environment subtly but fundamentally changing around them. This is our current predicament. Our technological infrastructure, our global communication networks, our navigation systems, our very concept of time, all are intricately linked to the Earth's rhythms. When those rhythms change, we must adapt or face the consequences. The journey into these strange phenomena is, therefore, more than just a scientific expedition. It is a profound meditation on our place in the cosmos. It forces us to confront our own vulnerability, our dependence on a planet that, despite our technological prowess, still holds ultimate sway over our existence. It reminds us that we are not separate from nature, but an integral part of it, and our destiny is inextricably linked to the health and stability of our planetary home. The Earth is not just a resource to be exploited. It is a living, breathing system, a complex symphony of interconnected processes that we are only just beginning to understand. What is required of us now is not fear, but a renewed sense of curiosity and a commitment to understanding. We must continue to push the boundaries of scientific inquiry, developing new tools and techniques to probe the Earth's deepest secrets. We must foster international collaboration, sharing data and insights across borders to build a comprehensive picture of these global phenomena. And perhaps most importantly, we must cultivate a deeper respect for the planet itself, recognizing its immense power and its profound capacity for transformation. The strange phenomena happening on Earth right now are not just facts. They are a narrative, a story of a planet in flux, and a testament to the enduring mysteries that lie beneath our feet and above our heads. And as we continue to unravel these mysteries, we are forced to confront the most profound question of all. What does it truly mean to be human on a dynamic, ever-changing Earth? The answer, it seems, lies not in conquering nature, but in learning to dance with its rhythms, to adapt to its changes, and to live in harmony with its profound and beautiful unpredictability. This is the ultimate challenge and the ultimate adventure that awaits us on our strange and wonderful planet. The ongoing unraveling of these strange phenomena is not just about understanding what is happening now. It is also about shaping the future of scientific research and exploration. Each new discovery, each subtle shift in Earth's behavior opens up new avenues of inquiry, new questions that demand answers. Imagine the next generation of planetary scientists, equipped with even more sophisticated tools and models, delving deeper into the Earth's mysteries. Will we develop new seismic technologies that can provide real-time imaging of the inner core's movements? Will our satellite constellations become so advanced that they can precisely map the geodynamo's turbulent flows, predicting magnetic field fluctuations with unprecedented accuracy? The challenges posed by a non-stationary Earth are also opportunities for innovation, pushing the boundaries of our scientific and technological capabilities. Consider the implications for space exploration. As we venture further into the cosmos, establishing outposts on the Moon and Mars, our understanding of planetary dynamics will become even more critical. Earth serves as our primary laboratory, a living planet where we can study the complex interplay of geological, atmospheric, and magnetic forces. The lessons we learn from Earth's strange phenomena will undoubtedly inform our efforts to understand other planets, to search for life beyond our own world, and to perhaps even terraform distant celestial bodies. The South Atlantic Anomaly, for instance, offers a unique natural laboratory to study the effects of increased radiation on technology and biological systems, providing invaluable data for designing radiation-hardened spacecraft and protecting future space colonists. The shifting poles and the fluctuating rotation rate challenge our assumptions about planetary stability, forcing us to develop more robust and adaptable systems for navigation and communication in the vastness of space. Ultimately, the story of Earth's strange phenomena is a testament to the enduring power of scientific inquiry and the insatiable human desire to understand our place in the universe. It is a narrative of constant discovery, of pushing the boundaries of knowledge, and of confronting the humbling reality that even our own home planet holds secrets that continue to baffle and inspire us. The Earth is not a finished book. It is an ongoing saga, a living, breathing entity that is constantly writing new chapters, revealing new mysteries, and challenging us to evolve alongside it. And as we continue to listen to its whispers, to decipher its complex language, we are reminded that the greatest adventures often lie not in distant galaxies, but right here beneath our feet, and in the invisible forces that shape our extraordinary world. The journey into the depths of Earth's strange phenomena is far from over. It is only just beginning, and the next revelations promise to be even more astonishing. Join us as we continue to explore the uncharted territories of our own planet, where the familiar becomes alien and the ordinary transforms into the extraordinary. The cosmos, it turns out, is not just out there. It is here, within the very heart of our home, waiting to be discovered. Throughout history, humanity has consistently sought to understand the world around us, to impose order on chaos, and to decipher the grand design of the cosmos. From the earliest stargazers who charted the movements of celestial bodies to the Enlightenment scientists who meticulously mapped the Earth's surface, each era has built upon the knowledge of its predecessors, gradually refining our understanding of the universe. Yet, with each new layer of discovery, we often find that the universe, and our own planet, are far more complex and mysterious than we initially conceived. These strange phenomena we've been exploring are a powerful testament to this ongoing process of scientific revelation, challenging long-held assumptions and forcing us to rewrite chapters of our planetary story. Consider, for instance, the concept of Earth's rotation. For centuries, it was understood as a relatively stable, albeit gradually slowing, process. The gravitational tug of the moon was the primary driver of this deceleration, a cosmic constant that shaped the length of our days over geological timescales. This understanding was built on meticulous astronomical observations and the elegant physics of Newton. But now, with the advent of atomic clocks and ultra-precise geodetic measurements, we are witnessing subtle accelerations, unprecedented shifts that defy this classical understanding. It's like discovering a hidden gear in a clockwork mechanism that was previously thought to be fully understood. A gear that is now subtly altering the entire rhythm. This isn't a refutation of past science, but an expansion of it. A deeper dive into the intricate nuances of planetary mechanics that were previously beyond our observational capabilities. It forces us to acknowledge that even the most fundamental aspects of our planet's behavior are subject to layers of complexity that we are only just beginning to peel back. The Earth's magnetic field offers another compelling example. For decades, the geodynamo model has provided a robust framework for understanding how our planet generates its protective magnetic shield. The churning, molten iron in the outer core, interacting with Earth's rotation, creates a self-sustaining magnetic field. This model has been incredibly successful in explaining many aspects of Earth's magnetism, including the occurrence of geomagnetic reversals over geological time. However, the emergence and rapid evolution of the South Atlantic Anomaly, coupled with the observed changes in the inner core's rotation, are pushing the boundaries of this model. It's like having a detailed blueprint of an engine, only to find that certain components are behaving in unexpected ways, suggesting hidden interactions or previously unknown feedback loops. These observations are not breaking the model, but rather enriching it, forcing scientists to develop more sophisticated simulations and theories that can account for these newly discovered complexities. It's a dynamic process of scientific discovery, where new data constantly refines and expands our understanding, revealing a planet that is far more alive and responsive than any static model could ever capture. And what of the Chandler wobble, that subtle, rhythmic oscillation of Earth's axis? For over a century, it was a predictable planetary heartbeat, a constant that provided valuable insights into the Earth's internal structure. Its sudden suppression between 2000 and 2005 was a scientific enigma, a momentary silence in a planetary symphony that had played consistently for decades. This event, linked to the massive redistribution of water due to ice melt, highlights the profound interconnectedness of Earth's systems. It demonstrates how seemingly disparate phenomena, climate change on the surface and the subtle wobble of the planet's axis, are intimately linked. It's a powerful reminder that our planet is a single, integrated system, where a change in one component can have cascading effects throughout the entire entity. These discoveries are not just adding new facts to our scientific textbooks, they are fundamentally altering our conceptual framework, forcing us to embrace a more holistic and dynamic view of Earth. The strange phenomena happening on Earth right now are not just isolated events. They are interconnected pieces of a grand, evolving puzzle. A puzzle that challenges us to rethink our relationship with our planet and to understand its intricate workings with a newfound urgency. The Earth is speaking to us, revealing its secrets in subtle yet profound ways. Are we listening? And are we prepared for what it has to tell us?